All right, so I'm gonna go over 2.1 first, and then we'll see 2.2. Hopefully, I'll complete two sections today's lecture. Okay, 2.1 is talking about matrix operations. Finally, okay. Mm, so we're gonna learn uh what's the addition and subtraction and the multiplication operation between two matrices. Okay. Okay, so we consider the matrix A is the A1 bar and A2 bar. So A1, A2, I mean A1 bar, A2 bar, these denote the column vector in matrix A. Okay, so let's say this is M by N matrix, for instance. Then in short, I mean shortly, we can the right A matrix A is like this. Aij. Okay. So or just bring open bracket and then lowercase aij. Okay. So like this. So normally the in subscript I represent the index of row, and then j is the index of column. Okay. So when you if you know if you know the programming, Python and C, normally we do loop for I goes 1 through n, and for j goes 1 through it should be m, right? And so the I is goes 1 through m. This is the uh the index of row, and the j is index of column, something like this. Okay, so if you are familiar with programming, I think you understand what I'm saying. Okay, so by the way, these columns, the columns of matrix A in what? In Rm space, right? Okay, columns are Rm space. Okay. Or you can write the matrix A as like this, A11. Okay, A1n. By the way, okay, sorry. If you're confused, maybe you're confused with this one, the statement, the columns of A are in Rm space. Why? Because how many entry in columns? Got it? So I just picked the A, for example, AJ, okay? AJ bar, take it. This is AJ bar is what? A1J, A2J, and then blah, blah, and the AMJ. How many entries? M, right? It's M by one column vector, right? So since there are M entry, that's why the columns of A in Rm space. Okay, so keep in mind that. So do not confuse with this one, because how many columns here? N entry, N columns. Then you may say that okay, column is in Rn space. No, the columns of A must be in Rm space, which is the number of entry, number of row is M. Okay, okay. Let me keep going. So here are A11, and then through the AM1, this is AMN, right? So this is A22, blah, blah, and then this is AM2, blah, blah, okay. Something like that. Okay, this is M by N matrix. Okay, and then the especially what? If number the index of row is equal to index of column, these entries are called the diagonal. Diagonal entries. Okay. And then, yeah, so in general, we can say AII, because the index of row is equal to index of column. So, and then I goes 1 through the, what? And in this case, what? The square matrix, if it means that M is equal to N, and number of row is equal to number of column, then, yeah, so we're going to get M diagonal entry, right? Okay. So if M is equal to N. Square matrix. This is called a square matrix. If number of row is equal to number of column, then we say that the matrix is square matrix. So, and then a certain matrix, let's say C, for example, and all of entry are 0, except for diagonal entry. Okay, so like this. This is called the square diagonal matrix. Okay, it's called the diagonal matrix. Definitely, yeah, it's assume that this is square matrix. Diagonal matrix. The two matrices are equal means that two matrices have the same sides with the same entries. All of the entry are equal. Okay. So then we say that the matrix, two matrices are equal. Okay. And then zero matrix, we saw that, right? All the entry are 0, then we say that the matrix is 0. Zero matrix. Okay. And the addition, and then yeah, see theorem 2.1. This theorem talking about the scalar multiplication and then addition of two matrices. So let's say matrix A, B, and C are, B matrices of the same size. Yeah, size right here. And let's say R and S be a scalar, and B be scalar. Okay, scalars. Okay, so this, just easy stuff. Okay, sum of two matrices. Okay, so here we assume that A, B are the same size. Okay, then this is equal to B plus A. How can I add two matrices? We just do the addition for each entries. And then A plus B is equal to B plus A. When you do add or subtract, this is called the just addition operator. When you perform the addition operator between two matrices, this is equal to, you can switch the two matrices. This is called the commutative property. The commutative property. I think it's English. I think in Korean is a 교환 법칙, something like that. Okay, the commutative property. Okay. So example is this. Let's say A is 1, 2, 3, 4. Okay, and then B is the what? Maybe -1, 0, 2, -4, something like that. Then A plus B is gonna be what? 1 plus -1. Because we do addition for each entry-wise, So 1 plus -1, and then 2 plus 0, and then 3 plus 2, and then 4 plus -4. So yeah, it's just easy, right? It's just straightforward. 0 and 2 and 5 and 0. Yeah. Subtraction is the same, okay? A minus B is do like that way. But A minus B doesn't satisfy commutative property. Okay, and then B, the A plus B, we do addition of two matrices, AB first, and then add the third matrix C. This is equal to A plus and then B plus C. So B plus C do first, and then we add a matrix A. Okay. This is called the associative property. Okay. Associative property. Then C is A plus 0. This is here, 0 means 0 vector. Okay, 0 vector is equal to A. Yeah. So now 0 is called the identity. Yeah, identity for the addition operator. do not confuse with the identity matrix. Okay, this is identity. So identity for the plus operation. Okay, I think this is the appropriate expression. So zero matrix is the identity for addition operator between two matrices. Okay. And then D, R times A plus B. Okay, so R is scalar, okay, real number. So this is equal to, then we can distribute R to each matrix matrices inside the parenthesis. So R times A plus R times B. So, so this is called the distribution property. Okay. Then also you can commute the R and A plus the A plus B. So that's the next statement. So R plus S times A. Oh, sorry, this is a little bit different from D. So this is R plus A, but this is A plus B. This is then still we can distribute matrix A. R times A plus S times A. Last one, the R times SA is equal to RSA. So, you know, basically the scalar multiplication of the matrix is pretty much the same as normally what we are doing in numbers among numbers. Okay. So that's just a basic stuff before we do this one, matrix multiplication. That's the main what the main contents in 2.1. Okay, matrix multiplication. Right. Uh, so think about this. Let's just consider A times B times X bar. Okay, let me use like X bar. Okay, bar is equal to A times B times X bar. Okay, I would just wanna observe this one. Okay, so how can you do A times B? I mean, matrix multiplication between two matrices. Okay, so first we set the size of matrix. Okay, let's say A be a matrix. Okay, R to the m by n matrix, and then B is in R to the n times P matrix. So A is m by n matrix, and B is n by P matrix. Okay, and then let's say X bar is x1 through the xp. Okay, this is in our P space, right? Okay, and then we denote A as this A1 bar, A2 bar through the AN bar. And then B is equal to B1 bar through the BP bar. Okay, then BX. Okay, let me do this. This B is a matrix. X bar is a column vector. So this is a matrix vector multiplication, right? We haven't done this one a lot in chapter 1, right? This is equal to what? X1 times B1 bar plus X2 times B2. Yeah, just simply, I mean, basically this is nothing but linear combination of columns of matrix B with the weight X1 through the XP in the column vector, right? So these are linear combination, right? So X2 bar through the XP and then BP. Okay, so this is linear combination, right? You got it? Follow me? Now it's just getting, more abstract and abstract, right? So, okay. So please, be careful So please focus on this one to catch up. Okay, if you lost, then you're gonna get big trouble. So, so now, let's, okay, so what we're gonna do is we wanna do this a times bx bar. Do this bx bar. Do this, and then finally we wanna get this a times b, and then x bar. That's what we wanna do. Okay, why we have to do this? So doing through this, you're gonna be familiar with the writing matrix multiplication and matrix vector multiplications back and forth. So a times bx bar is gonna be x1, right? b1 bar, which is, I'm gonna copy this. And then plus x2 b2 bar plus 30 xp and a bp bar. Okay, got it? So now this is equal to x1 is what? I mean, x1, x2, x through the xp are what? Scalars, right? So we can bring them out, right? Okay, okay, you didn't get it? Let me just, then keep going. This is a times x1 times b1 bar, right? Plus a times x2 times b2 bar plus 30 a times xp times bp bar. And now this is equal to, now since x1 through the xp are scalar, right? So we can switch them out. x1 times a times b1 bar plus x2 times a times b2 bar, right? Plus 30 xp times a times bp bar. Okay. So now this is equal to what? What we gonna get this? Okay. What's this? A times b1 bar. A is a11, I mean a1 bar, a2 bar, through the an bar, right? This is matrix A, and the b1 is what? b11, b12, through the b1, sorry, 21, right? 21, bn1. That's a b1, right? So this is A, this is a b1 bar. And this is equal to what? What is this? This is equal to b11 times a1 bar, right? Isn't it? Plus b21 times a2 bar plus bn1 times an bar. Linear combination. Give you example. Okay. Let me give you example. Let's say A is 1, 2, 3, 4. Let's say the B 1 bar. Let's say this is the two, not two, maybe 5 and 6. Okay. Then A B1 bar is equal to 5 times 1, 3 plus, okay, and then 6 times 2, 4. So this is equal to what? 5, 3, oh, 15, right? Plus 12, 24. So which is 17, 39. So what I did, this is what? Linear combination of vectors, right? So this is the what? Equals A1 bar. This is equal to A2 bar. That is what? This is linear combination. Combination of vectors A1 bar and A2 bar, which is A, with what? B1, 5, and 6. Right? Okay. So now back to the, okay, give me a second. Okay, so let's pick up where I left off. Okay, right here. So now we can say that this is a linear combination of AB1 bar and AB2 bar and through the ABP bar, because A times B1 bar through the A times BP bar are nothing but just column vector. You see that? AB1 bar turns out to be this. This is going to be a something vector. It turns out to be a form of column vector. So this is a column vector, this is a column vector, through the, this is a column vector. So we can say this is a linear combination of column vectors with x1 through the xp. So what I mean is this. This is, so we can say this is equal to A times B1 bar through the A times BP bar times x1, x2 through the xp. Okay. So now this is equal to what? Because A times B1 bar through the A times BP bar, this is equal to A times B, matrix multiplication. So times, this is what? X bar. Okay. So we know that we start with this. A times B x bar is equal to A times B times x bar. This is true. We already knew that. Okay. So now deriving this from this, we could figure out that, oh, A times B is nothing but this. Oh, okay, I see. A times B, matrix multiplication of two matrix AB, is, it turns out that this is A times the first column of second matrix, and then A times second column through the A times the last column. Okay, that's why I derive this from this to figure out what it is, what this guy is, A times B, which is this. So, okay, finally we got this. A times B is what? A times B1 bar, A times B2 bar, really? Okay, then A times BP bar. Okay. Okay. Now, so here's a note. So each column of AB is the linear combination of columns of A. This makes sense, right? Each column of AB. What's each column of AB? These are columns of AB, right? Is a linear combination of columns of A using the entry right in the corresponding column of B as weight, right? Of B as weight. Okay. So for example, let's say I pick the A times B J bar, then A times B J bar is equal to what? This is equal to B 1 J times A1 bar, right? Plus B2 J times A2 bar plus through the B this case N, right? N by N. So B N J times A N bar, something like this. Okay. So this means the linear combination columns of A using the entries B1J through the BNJ. This is the corresponding column of B as weight. Okay. Okay. So now here's a definition. Okay. Now we define the matrix multiplication. So, okay. So I hope you're familiar with this stuff. Sorry, this stuff. You need to understand. You should understand this. So definition, if A is n by n matrix, okay, let me just say A is n by n. Okay. And then B is n by P matrix. Okay. Then, and, and then AB is what? Is M by P. The AB gonna be matrix, but size is M by P. Okay. So with AB is A times B1 bar, A times B2 bar through the A times B bar. Okay. So now, and then here's a note. Actually, we can figure out the size of AB by looking at the size of A and B for each. So A is n by n, right? N by n. And then B is what? N by P. So now, the right there. So this is M, okay? And then this P, let me say this P, okay? Yep. Okay, MB. This one will determine the what? The size of matrix AB. Okay, so here M gonna be what? The number of, the sharp means a number, okay? The number of row, okay, of matrix AB. Okay, and then N, oh, the P, right? Here, P is what? Number of column of matrix AB. And then what about the N? So here, when you multiply two matrices, the column of first matrix must be equal to row of the second matrix. So here, fortunately, well, so here N are same, right? Must be same. Oh, let me do this. Okay, so right here, must be same. Okay. Otherwise, we cannot do the matrix multiplication. Keep in mind this. All right, so let's do, here's the example. Okay, so let me do this. 1, 2, 0, 1 times, okay, 3, 4, 2, 2. Okay. All right, so then what are you going to do? This is equal to, this is matrix A, right? Matrix A. And then we're going to look at this one as column-wise. Let's say this is B1 bar. Let's say this is equal to B2 bar. Then this is equal to what? A times B1 bar and the A times B2 bar, right? So now this is equal to, oh, yeah. So right here, A times B1 bar is going to be what? 1, 2, 0, 1. And then B1 bar is 3, 2, which is 3 times 1, 0, right? Plus 2 times 2, 1, right? You follow me? Okay. And do, what is this then? It's not a big deal, right? It's going to be what? 5, isn't it? 2. Okay. 7? Oh, yeah, yeah, yeah. Why is it 7? It's 3. Oh, 7. Yeah, yeah, yeah. 7. This is 2. Sorry. And then AB, oh, where do I put this? Okay, let me here. AB2 bar is, similarly, we can do that, right? So this is a 1, 2, 0, 1, and then 4, 2. It's going to be 4 times 1, 0, and then plus 2 times 2, 1. And then this is equal to what? 8 and 2, right? Okay, so this is the what? The first column of the matrix AB. This is second column of matrix AB. By the way, this is 2 by 2, right? Is this 2 by 2? This is 2 by 2. So the A times the size of AB is going to be 2 by 2 because what size of AB will be determined by what? Determined by the row number of row in the first matrix and the number of column in a second matrix, right? So this will be the number the number of row in a matrix AB. This will be the number of column in matrix AB. So now we got this. So what 7 2 and then 8 2. Okay. So now let's see example. So I'll give it time. So please do this is example 1. Okay, and then now this is example 2. So I'll give time. So please perform the matrix multiplication of two matrix 0, 2, 4, 1, 5, 8. So this is 2 by 3, right? And the second matrix is 2, 0, 3, and then 1, -1, and 4. Okay. So just do it. Just try it. Okay. Okay. So uh, what? All right. Okay, so in the last one, I'm going to introduce other way to do matrix multiplications. So this is row column rule. Okay. Okay. The first one, let's say A, B. A, A is a matrix and B is also matrix. Okay, A, B, I, J. This is I, J entry, which means that I row and J column entry of matrix AB, matrix multiplication AB. Okay, so this is equal to actually row of A and the I. What that means? This is the I row matrix A. Okay, and then dot product. This is dot product. Dot product is nothing but linear combination. Okay, so this is the row and the column, which means that this is the jth column of matrix B. Okay, so example, let's say like this. Okay, so example, let's say A is the 2, 3, and 4, 1. Then let's say B is the -2. Let me set the non-square matrix. Okay, so -2 and 0. Let's say B is, this is 2 by 3, right? Then B must be what? The size of B must be 3 by something, right? So 1, 1, 2, and then um, -2, 1, and 0, and 5. Okay, let's say this is a 3 by 2 matrix. Then we expect that the matrix multiplication of AB going to be 2 by 2 matrix, right? So we're going to get AB, which is the size going to be 2 by 2. Yeah, ABIJ. Sorry, say this is the ABIJ. and then size is gonna be 2 by 2. Okay. All right. So let's do this. The solution. We applying the row column rule. So then AB, the AB gonna be what? It's gonna be, let's say this is the I know this is gonna be, AB 1 1 and AB 1 2, right? And then AB 2 1 and then AB and 2 2, isn't it? So we're gonna find out each entry of AB by applying the row column rule. Okay. So AB this, so this is equal to AB 1 1 gonna be what? It's gonna be let's see. That's gonna be what? This 1 1 means what? First row of matrix A. Okay. So first row of matrix A. This is the first row of matrix A, right? And then first row column of matrix B. We do dot product of these two. What's the dot product? Dot product, everybody know about dot product, right? In Korean, dot product, 내적. So, which means that, so oh, let's see, 1, 2, 3. This is row vector. Then dot, give me a second. Let's say vector A, dot product B means that, let's say A is the 1, 2, 3, and then let's say B is 4, 5, 6, 5, 6, 7. Then this is gonna be just the linear combination. Yeah, you can say linear combination, but just the product of the sum of product of the corresponding the entries, which means that 1 times 5 plus 2 times 6 plus 3 times 7. Okay, that's called the dot product in DESA. Okay, so you'll study this one in the motion in 3D vector calculus. Okay, so now this one here, so we do dot product, which means that 2 times 1, 3 plus 3 times 1 plus negative 2 times 2. So we're gonna get what? 1, right? 1. And then AB sub 1 to subscript 1 2, which means that we do multiply the first row matrix A times the second row, second column matrix B. This and this. So 2 times negative 1 plus 3 times 0 plus negative 2 times 5. Okay. So you're gonna get negative 2 and then minus 10, negative 12. If I got it. And then 2, 1 means that the product, the dot product of the second row of matrix A. Okay. This is the second row matrix A time a dot product with the first row, first column of matrix B. This. So we got 4 times 1, okay, plus 1 times 1 plus 0 times 2. So which is a 5. The last one is a 4 times negative 1 plus 1 times 0 plus 0 times 5. So we got negative 4. Okay. So normally we do matrix multiplication following the row column rule. But you should know both this way and that way. Okay, this way too. The both. So please keep in mind that. Let me see. Okay, so here's a summary. Okay, the 3 view of matrix multiplication. So let's say A be a m by n matrix. Okay, and B is a n by p. Okay, okay, first one. Then AB ij is equal to row I and A dot product with just jth column of matrix B. That's a row column rule, right? The second one, the jth column of AB is A times BJ bar. Okay, which means the linear combination column of A using entry in BJ as a weight. Okay, or simply, or you can say jth column of matrix AB is equal to what? A times jth column of matrix B. We can say that simply. Okay, so this is what I introduced today. Two method. Okay, and then now last one, 3, is the ith row. What about the ith row then? Row of matrix AB is what? Then first row of matrix A dot the B1 bar. Okay. This is exactly the same as what? Okay, never mind. Okay, I don't make you confused. So this is row, and then I, then ith row of matrix A dot product with BP. Oops, I think this is the not first I. Sorry. Okay. So, or you can say this is equivalent to this. Ith row of matrix AB. This row matrix AB is equal to row ith row of matrix A times B. Okay. So please see examples in textbook. Okay. So because I don't have time, we don't have time to cover more in here. So because we need to move on quickly. So and then see theorem 2.3. So look at this. Okay. Here in theorem 2.3 is quite important. This is important too. Okay. So here you see the first one is this. Here, let's say A is the M by N matrix, and then B is N by P matrix, okay? Then this is A transpose, and transpose is equal to A. So what's a transpose? Transpose is this. Transpose is interchange row and column index, which means that let's say A be the 1, 2, 3, 4, okay? Then A transpose, we just change row and column, okay? So what's the index of 2? This is A1, 2, right? Which means that this is in first row, second column. So we interchange index of row and column. Then this will goes to this, right? And then what about then 3? Index of 3 is what? This is A2, 1. And then we interchanging. So we're going to then what? This will move to the first row and second column. So pretty much we interchange a row index or row index a column. Then we got this 1, 4, 2, 3. Diagonal entry will not be changed because diagonal entry, their index or row index column is equal or same. Okay. So that's called transpose. But here example one, okay, is example one. The example two. If A is the then let's say 1, 2, 3, and then 4, 5, 6. So this is the 3 by 2 matrix. Then A transpose is going to be what? 2 by 3 matrix. So 1, 2, 3, and then 4, 5, 6. So which is a 2 by 2 matrix. That's called the transpose. So A transpose equals, it's just trivial, right? And then B, and the A plus B transpose is gonna be A transpose plus B transpose. And then C, R times A, because R is scalar, okay? R times scalar transpose is just the transpose will not be effect on the scalar, okay? So R transpose is R because R is a single entry matrix with single entry. So yeah, it's for any R in real number. And then D, AB transpose. This is useful. Okay, keep in mind this is when you transpose the matrix multiplication, then you need to change order. B transpose and A transpose. So it's called reverse order. We just reverse order when you apply the transpose of matrix multiplication AB. Keep in mind that. Okay, keep in mind this. So now we move on. So I'm gonna if I have time, I'm gonna just prove this one next time. Okay, so we move on to chapter 2.2. Okay.